All right, everyone. Good afternoon. Okay, 6 of you come here. Okay. I know. I think quite a few students are still watching for the Zoom lecture. So I want to emphasize again, for the last homework, homework 5, please do it right now. We're here to help. And again, yesterday my office hour is still quite empty. Don't wait until the last day. I think I've announced. I've mentioned Canvas, right? Because the final homework, because I'm strict view from administration, we need to get the grade down before a certain time. So it's much less flexible to extend. And also, I think next week is the end of the whole lecturing procedure. That means after next week, we won't be able to provide office hours. So again, if you want help, try to leverage office hour. We have an office hour every weekday, like from Monday to Friday. And I think our TM, Shikai, is very diligent. He kind of, if there are many students, he tries to extend office hours until every student is satisfied, right? But that does not mean that he can help you and open office hours in Saturday on Sunday or at night. That doesn't make any sense, right? So if you want to seek for help, just come to the office hour, right? Don't try to come at the deadline, right? If it's due on Friday, you come on Friday. Of course, there are a lot of students, and you might be in a long queue, right? Okay. So anyway, we just want to emphasize that start early, and you will have plenty of time debugging your code. And I think the homework 4 and homework 5 are both problems about practice, right? So we have provided all the algorithm table. We have given the formulas, all the necessary formulas in the lecture slides. What you need to do is just to implement those algorithm table according to the slides and implement those calculation listed in the slides, right? We assume that you're able to do that, but we do suggest you to spend a little bit time ahead to debug, right? This is a programming, it's not just write down some mathematical expression, okay? Okay, so in the last lecture, we have finished the introduction of the base by backpropagation. It's a very straightforward application of the variational inference and the reparameterization trick, right? But this is reparameterization trick is a very important trick, although it's really simple. Right? So basically, if you assume your posterior is a Gaussian, right? I just use Gaussian as an example. And then you know your elbow, the evidence lower bound, which you want to maximize during the variational inference. Let me use D, give W, and Q of W, something like that, or log fractional of the joint distribution and the variational posterior and take expectation under Q of W. If you directly optimize this guy, if this whole evidence lower bound is not having some closed form, and a convenient way is that, okay, you're gonna reparameterize W by some standard Gaussian random noise, right? So this follows the linear property of the Gaussian random variables, right? Any linear combination of independent Gaussian random variables will be Gaussian again. So that means for this particular random variable, we can represent it as mu plus sigma half, and well, that basically means sigma half times sigma half equals to sigma, right? So times some standard Gaussian random variable. Standard Gaussian random variable means it follows a Gaussian distribution with zero mean and covariance I, right? Identity. And then you can convert this expectation in terms of the standard Gaussian distribution, right? And then you represent W in terms of epsilon here. And now you can do the stochastic optimization very easily. You just sample epsilon every time, then you substitute epsilon into this reparameterized evidence lower bound, and then just calculate the gradient, right? That will be an unbiased stochastic estimate, right? So someone had asked, what if it is not Gaussian? We mentioned that actually there are quite a few distributions. They have some kind of reparameterization trick, but might be a bit more, it might not be as straightforward as the Gaussian, like concrete distribution, like T distribution, like mixture Gaussian. Those kind of things are some kind of frontier research. Like if you, if you want to model your variational posterior with other form, right? Not only Gaussian, if you want to use a specific other form, can you come out some reparameterization trick? This is still the frontier research topic. And then we introduce the auto encoding variational base. This actually is just a probabilistic formulation of the, probabilistic formulation of this unsupervised learning, right? Suppose this is your image and this is your recovered image. Again, the autoencoding variational base aims to do the dimension reduction, right? You want to compress the data, like you have high dimensional data like images, right? This might be some image. I just random draw image. We don't want to store the whole image per pixel because it's so large. It's unnecessary to store all of them. So you want some like smart mechanism to compress this image into a very low dimensional representation, or maybe just a 10 by 1 dimensional vector is enough to preserve the information inside this image. So how can we learn this compression model, right? So we use two neural networks. One neural network will have this input as original image. Then the prediction is the low dimensional compression, right? This is called a encoder, right? It's called encoder. And then you got a decoder network where the input is your compression and the output is the high dimensional data, which has the same dimension as the original data. So this is called autoencoder. It basically means, okay, I want my original data through the encoder, I got some compression, and through the decoder, I can recover the original data as much as possible, right? This is called autoencoder, right? And the variation autoencoder is just the probabilistic version of this guy. Right? We haven't discussed in the class. I don't want to. I don't want to repeat this again. It's very simple and natural idea. Like you, in the modeling framework, you model the whole decoding procedure. You assign a prior over this latent representation, and through this decoder network, you predict or you reconstruct the original image. But then to learn the posterior distribution of this compression, low dimensional compression, you parameterize your posterior distribution with encoder network. So then you put them together to construct the variational evidence lower bound so that you can estimate the parameters for both decoder and encoder network. And it's very, very popular. And it's kind of, right now, it's kind of like standard approach to do this unsupervised learning or dimension reduction. Okay. So today we're gonna introduce another very cool and very widely used neural network. It's called general adversary networks. How many of you have heard of this type of networks? Okay. So what kind of applications have you heard about that? Yes, exactly. Okay. So it's kind of like amazing when it was invented. I think it was proposed in 2016 or 2017. It's said to be invented in a bar. Like several researchers from Google, they kind of like have some fierce debate about some project, and after their discussion from the bar, they came out this idea. And then when they wrote the paper, and then this paper becomes extremely hot. And right now, it's still there are every year a lot of works about general adversary networks. But very cool thing about very cool application of general adversary networks is indeed a style transfer. Like, suppose you got a collection of drawings from Picasso, right? Now, if you are given an arbitrary picture, which is taken by, say, your cell phone, like you want to transfer the style of the picture, that does not mean like you're gonna change the content. If you take a picture about this chair and desk, after the transformation, it's still a chair and desk, but you can see the style is kind of like drawn by Picasso himself. So it's very interesting application. Other than that, they use general adversary networks to compose music, right? Or even generate. Some guys use that to generate images or fake videos. There are like numerous applications examples in YouTube. Like maybe you can search in YouTube with the keyword deep fake, and you can see that how they can fake a video with this kind of techniques. Sometimes it looks like real. It really looks like real. Okay. So but we have to learn the general adversary networks in a more abstract and fundamental way, right? So if you get rid of those application side, if you take a look at formal definition of general adversary networks, what's the goal? What's the goal of GANs? What is the goal of the GANs? Right? So the goal is summarized as follows. So consider we got a uniform random variable x, right? But in general, you can assume you have some random variable sampled from any standard distribution. It can be from uniform distribution. It can be from can be generated from Gaussian distribution, whatever distribution, as long as you feel like I can easily use that distribution to generate one sample x. That's okay. And then we want to and now we want to find a transformation, right? We want to find a transformation like T, such that after applying this transformation over X, the transform variable, you know, because it's a function of a random variable, right? It will follow another distribution. And in most cases, we don't know what this distribution is. Like if you look at the pictures of cats, right? You know, give me your picture of cat, you know it is cat, right? But can you write down the distribution of the pixels in this image that describe a cat? It's very, very hard. It's very, very hard. And the goal of GANs is that, okay, it's very hard for me to automatically generate a cat image directly, right? So I want to know if I can find a smart transformation such that I can randomly draw a bunch of pixels. And then through my smart transformation, it can give me some kind of cat image. That's the basic goal of the GAN network. So this is actually a classical statistical question. If you have taken any statistical class before, we know there exists such a mapping. So basically, if your target distribution has some cumulative density function to be f, right, then your transformation or your mapping T should be inverse of f over x. And you can show that for x, if they sample from uniform distribution, then when you apply f inverse over x, then this transform random variable will follow the target distribution with density with community density being F. Right? This is just the standard conclusion from the statistical book, and it's fairly easy to prove that. And if you feel uncomfortable about this conclusion, you can try to prove that. It's a good practice of the statistics. Okay. But the problem is that in practice, we do not know the community density function of target distribution, right? As going back to the example we just discussed. Suppose my target distribution is just those distribution of pixels can guarantee you to generate some kind of cat image, right? Can you write down the CDF? You cannot write down, right? And it's even not sure. I'm even not sure if there is some closed form of CDF to cat image distribution. In that case, how can I learn this mapping T from data? Mm-hmm. For Gaussian distribution, yeah, you know CDF. Yeah. That's a good question. I wouldn't say it's a, well, it depends on how you define a closed form. Because the Gaussian CDF is a ERI function, which cannot be expressed by, junior functions. But we have a very accurate way to compute that. But in general, even okay, you are in favor of some kind of distribution, you even cannot represent it as a kind of knowing form. That's the major issue, right? And for example, if I want to generate an image which has the style of Picasso's style, right? How do you write down the joint distribution of the pixels which can guarantee you to follow Picasso's style? It's very hard. So the problem is that, okay, can we learn that? Can learn it from data. So although we don't know how we can mathematically write down the CDF or PDF of the target probability distribution, but we can collect data for that, right? We can have a set of samples from target distribution. This is much easier to get. For example, our target distribution are cat images. Right? I can collect a bunch of cat images, right? And if my target is this Picasso styles, images of Picasso styles, I can collect a bunch of Picasso's works, right? And then the question would be, okay, can I learn such a mapping T such that after the transformation, applying the transformation T over X, Tx, the transform variable, follows the target distribution. And this target distribution is reflected by the given examples. That's the question the GAN network wants to address. And in general, X can come from any convenient distribution. Of course, we use uniform distribution as an example, but as long as X comes from any easy distribution, you can compute, you can simulate, that will be fine. So any question regarding the goal of GAN? Everyone's comfortable with that? Because this is really important. We need to totally understand the goal of GAN before we get to the model and why they're going to design their training objective in that way. Okay, so again, GAN's aim is to learn a transformation, right, or mapping, such that after the transformation, the transform random variable will follow some underlying distribution in the training images or training data, whatever. Right?
So after training the network, even network random X, then it gives us a cat image.
Yes. Yeah, even you change X, right? Every time you sample another X, right? And it will generate another cat image. Like, of course, it won't be like give you exactly the same cat, but they always give you a cat.
Random.
Yeah, random cat. That's the goal. That's the goal, actually. Right, this sounds amazing, right? So you can imagine that from that, okay, I can fake a lot of things, right? Like I can fake a lot of Picasso styles images. I can fake music, like suppose it's composed.
Which does not exist in the world.
Yes. That's why the so-called deep fake applications was very hot for a while. You can take a look at that. It's really funny and really interesting. Many cool applications. Although I don't know whether morality we should support it or not. But indeed, it's kind of like a very powerful tactic. Okay. Now going back to the model itself, right? We know that we want to learn this mapping, right? And how do we model this mapping? We can use neural network. Neural network we know that it's very powerful. It can approximate nearly arbitrary functions. So it's natural to assume T can be represented by a neural network. Yeah.
So the combination of GAN and most of the sample you can give us a network simulating our distribution.
Yes.
You can use first MCMC to produce some samples, and then you use that samples to train GAN. And finally, you can use GAN as a much easier, much cheaper way to produce the data.
That's exactly. Yeah. So yeah, we can. Now that you mentioned this question, I can give you a little bit more concrete procedure, like how do we transfer the style, right? So you can imagine your X will be some ordinary images taken by any of your cell phone or your camera, whatever. Right? This is X. Right? So your training set for GAN will be a bunch of a collection of works from Picasso. So the goal will be, okay, I'm gonna learn neural network transformation. After transformation, T over this X, it's gonna convert the style of X such that this style is the same as a Picasso style. By style, I don't mean they should be exactly the same. It just means the same style.
From another aspect, our goal was to, we were not able to generate samples from directly from the institution.
No, you cannot.
Yeah, but we used MCMC to do that.
I wouldn't say it's MCMC. It's actually in the training procedure. Every time you're gonna sample X randomly from this standard distribution. Well, you see, you can call it Monte Carlo, but from the optimization perspective, I would be more confident to say it's kind of a stochastic optimization. Like every time I just randomly generate the X sample from this standard distribution, and then apply my faker network, which we're going to discuss later. And then I want my police network to rate it as very similar to the target distribution as possible. But it's kind of like gaming procedure. At the beginning, the police network or the discriminative network will tell you, okay, this is very different from the target distribution, and then you're gonna adjust your generator network and to make it more and more similar to the target distribution. Any other question? Okay, so as we mentioned earlier, we want to learn this mapping T. So it's very convenient to assume T is represented by a neural network, right? And then the learning is to identify the parameters of this neural network. Right? So basically, you can view like, okay, this is your original, your standard distribution, which might be uniform, right? This is your target distribution. And those red circles are just samples from the target distribution. Corresponding to our case, or to our examples, it might be a collection of Picasso's pictures or a collection of cat images. Right? And this guy, there's no need to give you training examples. You can generate by yourself because it's just the standard distribution. Could be Gaussian, could be uniform, whatever. And our goal is that, okay, want to learn such a neural network that if you just randomly generate a bunch of samples from the standard distribution after the transformation of neural network, the distribution of the transform variables will follow the same distribution as those red dots does. Does it make sense? But how can we learn that? It sounds a non-trivial problem. So the key idea of this again is called adversarial training or the gaming. It's actually this idea, kind of high-level idea has been used in many years. It's just called gaming or adversarial training. Specifically, we're going to introduce two neural networks. One is called the generative network or faker network. So basically, the faker network is here, is the T. And faker network is in charge of converting sample from standard distribution into the sample from the target distribution. Of course, at the beginning, if it is not well trained, we cannot do that, right? So to push the faker to fake examples of target distribution better and better, we introduce another network called discriminative network or police network. So we want the faker network growing stronger and stronger, same time police network growing stronger and stronger, such that we finally end up with an excellent faker. So that an excellent police network, even an excellent police network cannot differentiate the image is generated by the faker, generated by the target distribution. That's the idea. So I got a faker, I got a police network. I want to make both networks strong. Right? And you can imagine a police network, at some point, it can be very accurately differentiate if this particular example belongs to the target distribution or not. At the same time, if I can make my faker network powerful and powerful, right? More and more powerful, I can generate an example almost exactly follow target distribution, in that even this strong police network cannot differentiate from the true target distribution. Does it make sense? So this is the idea. So how can we fulfill this? By the other any question, I'm just telling the general idea. We're going to getting into the detail in a minute. But before that, I want to make sure everyone feels comfortable about this kind of adversarial idea or adversarial training or gaming idea. Everyone comfortable? Avoid being cheated. Yeah. It's like yeah, like this guy, like this faker. This is the police. They're kind of fighting with each other, right? Like they want to try the faker wants to try his best to successfully cheat the police. And the police network wants to try his best to identify the cheating, right? And when you comes to some balance point, we expect the balance point will be, okay, the police is very, very powerful police who can successfully differentiate fake examples and true examples. Right? By true example, I mean it is really generated from target distribution. But my faker network is so strong such that it can generate examples exactly follow the target distribution. That means even an accent police network cannot differentiate. And then the question is, how shall we fulfill this idea, right? In this in the training procedure. Oh, by the way, I want to make it more concrete. So this is a generator network, or called figure network, parameterized by W1. This is a discriminator network or police network, parameterized by W2. And those are data samples coming from the target distribution, like a collection of cat images, a collection of Picasso works, right? So you can imagine this whole gaming or adversary training procedure is as follows, right? So first, you randomly generate a sample from the standard distribution, Z1, right? Then you use that, make transformation. That's the way you generate the faked image, right? So you feed this faked image to the police network. And the police network immediately identifies this is a fake example. It doesn't follow the target distribution. So it gives you a negative a warning. And use this label or warning information. This is essentially supervised information for the generator network. They're gonna improve the network. That means they're gonna update the weights in its figure network, right? And then it tries to deceit or cheat the police network again, right? To generate another sample Z2 from the standard distribution and make the transformation, get a fake example and feed it to the police network again. And unfortunately, the discriminative network successfully identifies the cheating again and give you this signal. Based on that signal, which is essentially a supervised signal to the generator network, so the generator network can use that to improve itself. So keep doing this, keep doing this. At the same time, because every time we throw out some fake example to the discriminative network, so you can imagine this faked images plus the samples from the ground truth distribution, target distribution, also form a supervised signal. So that means in the meantime, the police network is updating itself as well. So this is growing as well. So you just do this back and forth procedure until finally your generator network, when they send his newest faked image to the police network say, okay, I cannot differentiate. I believe this is true. That's the whole procedure. Mm-hmm.
Network is not trained, so
of course, at the beginning, you just randomly initialize W1, W2, right? They give you all kinds of absurd results. But as long as the training procedure proceeds, remember, discriminated network always has the training examples from the target distribution. It tries to make it powerful, more and more powerful. And meanwhile, the generator network will receive more and more clear signals from the police network, and then it improves itself. And then it kind of like, you can view like kind of a co-training procedure. They both update their parameters and make their prediction more and more accurate. And finally, end up with this balance point. Mm-hmm. Yes. How should I see that? It can provide both the label and score, because if you predict label, of course, it gives you score first, right? And later we'll see that the likelihood essentially is computed based on the score, because it's the Bernoulli likelihood. I will see the objective function in a minute, and then we'll see that. Other question? Okay, great. So Another thing we want to mention is that this Z from the standard distribution can be generated from any easy distribution, and they are not necessary to have the same dimension as the output. So basically, if you want to fake an image, right, you know that image itself is a high dimensional data, right? But the latent variable Z, which you use to fake an image, is not necessary to be high dimensional as well. It can be just two-dimensional, not two-dimensional. It can be 10-dimensional or 20-dimensional. Is relatively low dimensional. Of course, which dimension is the best? It is really depends on the application. You have to choose by yourself. Okay. So, oh, by the way, so the generator network, the input will be this samples from any easy distribution, and output will be the whole data you want to fake, typically an image. But for the discriminator network or police network, the input is the whole image, which is relatively high dimensional. But output will be a probability. Probability is this is true or not. Probability true being true means that okay, he believes this input X indeed comes from the target distribution. So you can simply view the police network as a classifier, like logistic regression, right? It predicts whether this input image comes from a target distribution or not. Right? So this probability means the probability that the candidate can be considered as a sample from the distribution that produces the training examples here. Is it more clear now about definition of the police network? No, the training examples always, you can imagine that if they are well trained, they will always predict the training examples as label 1, meaning that, or their score will be approximately 1 or near 1. That means that, okay, I believe the probability that those examples come from the target distribution is very, very high, right? But at the same time, they're gonna also test if an arbitrary other image belongs to the target distribution. Of course, if it is very far away from target distribution, then it will give you a very low probability score. Does it make sense? Okay. So now, here comes our training objective, how to combine the faker network and the police network. So actually, this is a minimax problem. So it's not maximization nor a minimization. It's a minimax. That's why it's called gaming. So the gaming procedures always tries to address some stationary saddle point problem, really represented by minimax. Okay, so first, let us look at the first term. Right? So this guy tells us, okay, if I sample data point from empirical distribution based on the training examples. So basically you can view like, okay, if I randomly sample an example from my training data, then what is the log probability of the police network? The police network, remember, given the input, it will predict the probability this input image belongs to a target distribution, right? So that just means the log likelihood of the training data. Right?
Well, you can, yeah, you can think in that way because we don't need to calculate entropy of the empirical distribution. Yeah. But here I want to express it. I want to explain it in another meaning. Right? So if you take a look at the min-max procedure, right? If W1 fixed, meaning that the Faker network is fixed, you want to maximize the objective in terms of the police network. And W2 corresponds to the police network parameters, right? So that means this guy, because we maximize the whole thing with respect to W2, we want this guy to be as large as possible. What does it mean? Why we want this guy to be as large as possible? Yes, exactly right. Remember the police network essentially is classifier, right? And all the training examples, because it come from the target distribution, so they are all positive examples, right? So you just want your log probability. The prediction of the police network is just the probability. It is from the true distribution, right? From the target distribution. So you want this score to be as large as possible. You want to maximize the likelihood of these positive examples, right? And again, let us continue to fix the Faker network, just to look at the maximization procedure, right? Now let us look at the second one. And of course, we want to maximize the second one as well, right? When we fix W1. Fix W1 meaning that, okay, our Faker network is here, it's fixed, right? So you can see that you're taking expectation or Z from the standard distribution with which our Faker network will fix things, right? And the output of this Faker network, given the input Z, is actually the faked examples, right? So this guy just means this one minus this guy just means the probability that your police network think it is false, right? It is faked things, right? So we can view like, okay, the second term essentially is the likelihood for negative examples. Right? So you got positive examples training from the whole training set, and you got negative examples generated by your Faker network, right? So you just want to maximize the whole likelihood. That's how we improve our police network. Does it make sense? Okay. Now, we have explained why it is reasonable to train a police network, meaning doing this maximization procedure. Now, suppose our police network is fixed. To train the Faker network, our goal is to minimize the whole objective. Okay? So since our police network is fixed, so let us just assume, okay, this kind of constant to W1, right? Or we only need to care about this guy. So when we minimize this guy with respect to W1, namely the Faker network, what does that mean? Yeah, it's trying best to cheat the police network, right? You minimize this guy, you minimize this guy with respect to W1 is actually increase this guy, right? Increase 1 minus this guy. You actually decrease this guy, right? So it's actually, it's just to increase the likelihood of your negative example. And it make it oh, sorry, I might put the wrong direction. Right? So you want to minimize this guy. Essentially, it is equivalent to you maximize this guy. Right? And this actually is the score that your police network think this fake example is true. You want to increase that score as much as possible. And in the ideal case, you even want this guy to be 1, right? That means you completely deceit the police network. Right? So here is where the gaming happens. Right? On one hand, when you do the maximization with respect to W2, you're trying to differentiate the positive examples generated from the target distribution and the negative examples generated by the faker network. Right? On the other hand, we minimize the whole objective with respect to the faker network. It tries to mingle these 2 types of examples and let the police network harder and harder to differentiate them. That's the whole philosophy of designing such kind of objective function. Any questions so far?
Then W1 is fixed, is just classification.
Yes.
It's the distribution is a mixture of empirical distribution and the transform distribution T. Why? Then we want to try to make the network to classify it as good as possible.
Yes.
And then we try to minimize W1 to.
Yes. Yeah. If I write down what you said, it's like that. So at the beginning, we got a target. I got a target distribution, something like that, right? And the faker network will generate faked images, follows very different distribution. And you're gonna train the police network. It's very easy to find the classification boundary, right? To well separate them. And then it can tell you, it can warn you, okay, all you did is just fake images. Through that information, the faker network will evolve, will do some evolution, right? And try to fake a bunch of examples, right? To make it to make the distribution of fake images getting closer to the target distribution, right? But in the middle, in the middle step, there still can be clear boundary to separate them out. That's how we make our police network stronger, right? But at the same time, this discriminated information will enlighten the faker network to further improve it, and it will generate the images or faked images closer and closer to the target posterior. And finally, you can imagine they're going to generate a bunch of images kind of like behave the same pattern as the posterior distribution. In that way, it's very hard to find a classifier to differentiate them. That's you can view the training is like the whole training procedure is evolving in that way. It doesn't matter. Later we'll talk about the naive implementation is called stochastic minimax. So basically, you fix W2, you do stochastic update with respect to W1. You fix W1, you stochastic update W2. Just do this alternating update. But the state of art is called a Wasserstein GANs. If you're interested, you can take a look at it. They get rid of this minimax. They point out some issue of this minimax, the stochastic minimax optimization issue. So they use another type of optimization technique, and those are the state of art right now. Yeah. Okay. Yeah. And then when it comes to the training procedure, as we mentioned, it's called minimax stochastic optimization. It is the original algorithm proposed in the first GAN paper, and it was like very popular and very easy to implement. So it's kind of dominant GAN research for quite a while until the Wasserstein GAN comes out. If you're interested, you can take a look at that. But here we're gonna just talk about the fundamental algorithm. So how can we learn the parameters of the two neural networks, like police network and figure networks. Right? So we just go through many iterations, right? From iteration 1 to iteration big T. Right? And inside each iteration, we just go through key steps. This is to update the police network. Like remember, if we want to update the police network, it's kind of messy. Let me just erase them. That means you fake W1, you just maximize the summation of these two terms, right? Two expectations. So as we mentioned, we should use stochastic optimization. So that means we can sample a bunch of examples from this empirical distribution and sample a bunch of examples from the standard distribution Z, right? That's where these two steps are doing. Sample a mini batch of M samples from the standard distributions, or from a mini batch of M samples from the training data. Then you update the discriminator parameters W2 with stochastic gradient ascent. Why it is ascent? Because we want to maximize the loss, right? And after we have updated the police network, we're going to fix police network parameters. Then we update the figure network. And in updating a figure network, because this guy has nothing to do with figure network, right? So don't need to worry about that. What you need to do is just perform a stochastic optimization with this guy, right? And again, we're going to sample a bunch of examples from Z, and then calculate the stochastic gradient and update W1 accordingly. And now we're doing stochastic gradient descent. Why? Yeah, because in auto level we're doing minimization. So remember, this is called a stochastic minimax. You need to make sure one step is doing gradient ascent, the other step is doing gradient descent. And you just do this alternating stochastic gradient ascent, stochastic descent until all the big T steps are finished. And in theory, they're still guaranteed to converge to a saddle point with probability 1. But in practice, people are often just set up a maximum number of epochs or iterations and then stop. And then finally, you return these two networks. Okay, any question regarding the algorithm steps for GANs?
Negative sampling.
What?
Negative sampling.
Negative sampling.
Yeah, it's similar to that. At least in the first step.
Yeah, you can see it as a kind of negative sampling, but usually, usually when we see sampling like negative sampling or positive sampling, it just means if your data are imbalanced, you want to downsampling one part. But here, yeah, in that way, yeah, you can view it that way because in a minimization of the minimization step, you only sample Z, right? You don't need to sample X. That's where you can still view, because from the police network's point of view, those are negative samples, right? Okay, yeah, that's a good point. Yeah. Other question? Okay, great. I believe everyone knows. You guys should be able to implement again by yourself, although it's not in the homework assignment. And if you're interested, you can try to do that and say if it is really that fascinating, right? And also you can take a look at the WGAN. Almost right now, all the like mature libraries implemented WGAN. It is said to be more stable. Right? Okay, so here is some kind of illustration of the GAN training procedure provided by the original GAN paper. So this is the beginning step. So you can view this blue curve as the distribution of the faked images generated by the faker network. And those black dots are just the training examples. They all come from the target distribution. So you can see that these black dots form, you can see the shape of the target distribution, right? So the beginning, through some transformation of the standard random variable z, the distribution of those fixed images, which is the green curve, is far from the target distribution, right? Represented by those black dots. And those dashed or dotted blue curves are actually the scores provided by the police network. So you can see that if examples coming from the target posterior, which is this black curve, and it is give you a relatively high score. But if it comes from the Vickers network, it gives a relatively low score, right? And then you can see how this training procedure are evolving, right? So of course, at the beginning, they're all very bad. Even for the police network, you can see this kind of perturbation is not very good. Right? And then after a few kind of training, you can see that first the discriminator or police network gets much better. For examples, most likely come from this target distribution. It gives a very high score. For examples, most likely come from this Vickers network. It gives very low score. And then guided by this scores, the Vickers network tries to make or fake new examples who follow a distribution get closer to the target distribution. You can see the green curve is approaching the black, right? And at the same time, the police network kind of like get updated as well, right? So they can still give a very high accuracy when examples come from here, but then it is come from here because it's harder to differentiate if this example comes from the Vickers network or comes from true distribution. So the score comes drop, right? And finally, when the Vickers network generate examples, its distribution exactly overlap with the target distribution, well, the police network is no longer able to differentiate them. Okay, so I want to give some concrete examples to show what's the result of the game. Actually, it's quite amazing. So they give in their original paper, they give they give four different set of images. So those left-hand side, those guys are the training images. Meaning that, okay, well, I want to train a Vickers network that can generate numbers, right, with the same style as the training numbers, training digits. And those yellow ones, I mean, yellow frame, are the generated images. And those are not copied them, right? You can see that it's not a copy of the training images. Even they generate the same image, there's still some difference there, because they are directly mapping of some uniform random variable to those different digits. So you can see it's quite amazing, right? And also, here's actually where the technique of deep fake comes from. They also have a collection of the physics, right? These are this left-hand side things are just the training physics, right? You got a bunch of physics, then you scan to train a Vickers network from some noisy distribution, say a Gaussian distribution or a uniform distribution. They can directly generate different physics. Right? So you can see that those are valid physics, right? It looks like normal physics, and those physics not directly copy any of them from the training data. So that's very interesting. But I just want to mention that it's not always guaranteed you're going to generate a valid face. So there could be the cases you got 3 eyes or 2 noses there definitely are some failure cases, but in many cases, they can give you some amazing results. Right? And this example are generating, I think, are different types of animals. Yeah, different types of animals. I'm sorry, there's the resolution here is really low. Maybe it's just because I copied and pasted them in the PDF version. But anyway, they all generated new images, but still follow the style of the original images, and they are valid. So now this is the example of the style transfer. Right. So this is the input image. Right? So you can, as we mentioned, like in this case, our Z, the standard distribution, will be represented a bunch of normal, ordinary images. The training collection would be a bunch of a collection of works following for some particular painter's style, like Picasso. Of course, Picasso's style is really unique, but you can definitely mimic other, like Van Gogh, right? Like you can definitely mimic that kind of style. I do see some works doing that. That's very interesting as well. But anyway, so those are the training images, and those are the input. You can view it as a random noise, but this random noise is just ordinary image. Right? And then after the training, they can convert it to this image, right? So you can see that the content doesn't change, but the style is changed. And so that's very interesting. That stimulates a lot of like the computational modern art, because they got a new branch, kind of cross-discipline. You can use computer, you can use artificial intelligence to help you create new works, but you can decide if it is a good thing you want. You can even try to adjust the parameters to fine-tune that. Actually, last year I was reviewing some paper, like it's called multimedia, IE multimedia. It's kind of a top journal in a multimedia domain. There are a bunch of works telling you how to do this style transfer in a GAN framework. It's very interesting because I've never done any works about multimedia or arts, but now look at their work. It's nice actually. But again, there are many funny examples online. If you're interested, just search in YouTube. There will be many such kind of instances and you can enjoy. Applications like deepfake, style transfer, and composition, and especially deepfake videos. And they can fake video and made by some politicians, but actually it's not made by that politician. There are a bunch of examples you can see. You can find it in YouTube. Okay, so now we have wrapped up the Bayesian neural network. What we expect, right? So first, we expect definition of Bayesian neural network, right? How do we formulate neural network in a probabilistic framework? Actually, it's pretty straightforward. You just assign some probability prior distribution over the neural network weights. Then you create a joint probability over the neural network weights on the data, right? And that's about modeling. Then how to do the training in neural network. So you should know the concept of backpropagation and the commonly used technique to train the neural networks, which is called stochastic optimization, right? And then by leveraging stochastic optimization idea, how do we conduct the variational inference for Bayesian neural networks, right? Especially how to combine with the reparameterization trick, because it's so important in the future. If you want to do, if you happen to do some research related to Bayesian learning, no matter if it is a neural network or not, you're going to use reparameterization trick because it's very convenient. And also, we want you to understand the key idea of Bayes by backpropagation, the variation autoencoder, and GANs. And we hope, we believe that you should have already been able to implement them by yourself, by yourself, although you might don't have time to implement again or autoencoder. Right? In our homework, we just ask you to implement Bayes by backpropagation following the algorithm table we gave in the lecture slides on a very small data. Hopefully that will be a good practice to give you some concrete ideas how these things are applied in practice. Okay, any questions so far?
Is it possible to use this kind of method again to implement online translation?
Online what?
Online translation.
That might be a good idea, but right now the state of our online transition is not based on GAN. It's based on the what? Yeah. It's a yeah. Of course, but I mean, it's like sequence to sequence. So
Voice.
yeah, text translation, voice translation is all. I mean, the state of art. I'm not saying this is not feasible. I'm saying like the most popular technique of state of art is trying to learn a sequence to sequence mapping, and you have to involve recurrent neural network. Right now, people because we don't have to introduce recurrent neural network, but it's just another type of neural network, and you have to model the dependency between the successive words or phrases. That's why you need to introduce some sequence model. And then right now, to save the computation cost, then they introduce the so-called attention mechanism. To me, attention mechanism is essentially another way to implement kernel, but using attention will overcome the issue of the recurrent neural network. Those are like a kind of a state of art, but it's possible that they also apply the GAN, the training principle of GAN, like some gaming procedure into that process. Any other question? Okay, is everyone comfortable with all these things? Okay, so I think we have still we have 10 minutes. We're gonna start with the last thing in our semester. It's called Gaussian process for regression, and we're gonna give a brief introduction of Gaussian process for regression. And in the next lecture, I think that it will be the last lecture of this semester. We're going to introduce the connection between Gaussian process and Bayesian neural network, and then we'll give a quick review of what I have discussed so far to give you like more systematic view of the content in this whole semester. Okay. So what is Gaussian process for regression? Actually, I love Gaussian process for regression. I use Gaussian process more than Bayesian neural network. Unfortunately, I guess we can only put it in the end of this schedule, because right now every people is turning to neural network. Right? We don't want our students to miss the train, right? But actually, Gaussian process is also a very powerful model, and along with Gaussian process, there's a large domain. It's called the Bayesian nonparametrics. It's very elegant. It's very elegant topic. They use stochastic processes to model things. Very nice mathematical properties, but it's much harder to learn. Okay, so by the way, for Bayesian nonparametrics, we're going to only introduce Gaussian process regression. So you see that Gaussian process regression essentially is a kind of probabilistic interpolation. So we'll give a introduction about how to train a Gaussian process regression model and how to make a prediction. You see that this is very convenient because you assume everything follows Gaussian distribution. And finally, we want to highlight the connection between the Gaussian process and Bayesian neural networks. Actually, many theoretical analysis of Bayesian neural networks are based upon the structure of Gaussian process. Okay, so first, what is Gaussian process regression? So Gaussian process regression is used to learn functions from data. Of course, using neural network is also aims to learn function from data, right? But what's the difference, right? So Gaussian process tries to assign a prior over a whole function curve. That's kind of like easy to make people feel like confused, right? How do you assign prior over a function curve, right? But the idea of Gaussian process is that, okay, I want to assign a prior over functions. Then after I have observed a finite set of values of the function at different inputs, I want to calculate the posterior distribution of the function curve. That's the idea of Gaussian process. So in general, we can assume we want to learn a function where your input is d-dimensional, the output is just a real value, right? So you can view if you use Gaussian process prior to sample function, it will give you such kind of curve. If you sample multiple times, you have a multiple such kind of curves. From what we have discussed previously, we know how to place a prior over several random variables, right? If you have m random variables, we can assign a joint distribution over this m random variables, or you can assume they're factorized, whatever, right? But here, how to construct a prior over function itself? The function actually is a collection of infinitely many variables, right? And those variables are usually uncountable. So an intuitive way to extend or generalize prior over finite set of variables to infinite set of variables is as follows. Right? We can still view a function as a big table. So you can imagine one column of this table are all the possible inputs, and the other column of this table are the corresponding function values. You can view each particular output, that is the function evaluated at one specific input, right? This is a random variable. And then we want to place a prior over the whole column, the output column. And that's the goal of the Gaussian process, a prior, right? But how do we fulfill that? So for the function, one thing we should be aware is that the possible inputs of function are usually infinite and uncountable. So that means this output you can view like infinite uncountable set of random variables. How do I assign a joint distribution over that? Right? So then we need to use the so-called random process. So if you want to model a particular random variable, right? Meaning that the random value is some real world value, well, you can assign distribution. Right? However, if you want to model the distribution for function curve, right? That means an infinite uncountable collection of the values indexed by inputs, then we usually use a random process. So what is random process? So we can basically, if we kind of record what we have reviewed before, the random variable is actually not some value, it's a mapping, right? Remember, the random variable is essentially is a mapping from some probability space to some real value space, right? So probability space contains the sample space and the even space and the probability measure, right? The sample space is all the atoms, and the even space essentially is a sigma algebra. Forgive me, I have to bring out this jargon again, but this is how you understand the difference between the random process and the random variable. Right? So a random variable actually is a mapping from the sigma algebra to I will say really it's called Borel set That means if you're in a mapped space, if your sample set is just a real space, and based on real space, you can construct a sigma. Oh, sorry, it's not sigma alpha. Okay, it's just a map. It just map the Borel. It just map the sigma algebra to some real space. So you can will like this sigma algebra contains all possible events, and then each event corresponds to a real number. So this mapping is called random variable. And that's why you can see some textbook write random variable as x omega. Omega actually is some element in a sample space, right? That's how we define random variable, right? But how we define random process? If the mapped space is no longer real space, it's a function space. That means every element is a function. Then it's called random process. So you can imagine like here, this omega comes from the sample space in the original probability space, right? Now, for each omega, you map it to a particular function curve. This mapping is called random process. And because it has the random source comes from this probability space, that's why you have some randomness over this function curve. So that's the difference. This is the difference. I mean, the underlying definition, the difference lies in underlying definition. It's just you change the target domain when you define the random variables. Right? And but later, I think we should stop here today. But next Tuesday, we'll just give a more concrete example to show the difference between the random process and random variable. Okay, see you on next Tuesday.